In June of 1667, a French physician named Jean-Baptiste Denis walked into a Paris room and did something nobody had ever done to a living human being. He pumped lamb's blood into a sick boy's veins. The boy was 15. He had a fever. Doctors had already bled him 20 times trying to cure it. He was dying. Denis picked up his equipment, connected a tube to a lamb standing nearby, and pushed roughly 12 ounces of animal blood into the boy's body. The boy survived. Denis celebrated. The French medical world erupted. And then, within 18 months, a man lay dead on Denis's table. A woman stood trial for murder, and the French government banned blood transfusion entirely. That ban lasted 150 years. The strange part, nobody understood why it had gone so wrong. Nobody could, because the thing that separated a transfusion that saved a life from one that ended it was completely invisible. Too small to see, too new to imagine. It sat hidden inside human blood the entire time, waiting for the right person to look in the right place. That person wouldn't arrive for another 240 years. But to understand what he finally found, you first need to understand what everyone before him got wrong. And they got almost everything wrong. Starting with the most basic question of all. What is blood? And what does it actually do? For most of recorded history, the answer was dramatic, deeply symbolic, and medically useless. Every major civilization in the ancient world treated blood as something close to the essence of life itself. The Egyptians linked it to the soul. The Hebrews forbade drinking it because life belonged to God. The Greeks and Romans poured it in sacrifice and read its patterns in divination. Blood meant power. Blood meant identity. Blood meant something that went far beyond a fluid moving through the body. That symbolic weight made blood fascinating. It also made it nearly impossible to study clearly. The medical framework that dominated Western thinking for 2,000 years came from Hippocrates, the Greek physician whose name still echoes in the oath doctors take today. His model divided the body's fluids into four humours: blood, phlegm, yellow bile, and black bile. Health meant these four stayed balanced. Disease meant they didn't. And the central weapon against disease, the treatment prescribed for fever, infection, headache, mental illness, pregnancy complications, and essentially everything else, was bloodletting. Deliberate removal of blood from the body to restore the balance. Physicians bled patients with lancets. They applied leeches to the skin. They heated cups and pressed them against scarified flesh to draw blood to the surface. They did this confidently, consistently, and for roughly 2,000 years without meaningful challenge. Then, in December of 1799, they did it to George Washington. Washington fell ill with what was probably a bacterial throat infection. His physicians bled him 5 times over 12 hours, removing somewhere between 5 and 7 pints of blood. He started with roughly 9. By morning, his heart had nothing left to pump. The treatment killed him faster than the disease would have. But here is the critical thing to understand. Nobody in that room thought they were doing anything wrong. The humoral framework made bloodletting rational. If blood was corrupt or excessive, removing it fixed the imbalance. The logic was clean. The theory was coherent. And it was built on a foundation that had one enormous problem. It was completely wrong about what blood actually did. Then William Harvey changed everything. In 1628, Harvey published a small book called De Motu Cordis, on the motion of the heart. His argument was precise and revolutionary. Blood didn't pour in tissues the way humoral theory suggested. It circulated continuously. The heart was a pump. The vessels were pipes. Blood moved through the entire body in a closed loop, driven by every beat. The implications took decades to fully absorb. But the most important one was this. If blood circulated through a closed system, then in principle, you could add to it from outside. Lost blood might be replaced. A dying patient might be saved. That idea sat in the air for a generation before anyone picked it up and ran with it. First came Richard Lauer, an Oxford physician with a steady hand and a willingness to try things that had never been tried before. In 1665, Lauer connected to dogs with quill tubes. He bled one dog nearly to death. Then he opened a channel from the healthy dog's artery into the dying dog's vein and let blood flow between them. The dying dog should have collapsed. Instead, it steadied. Then it recovered. Lauer repeated the experiment. It kept working. The Royal Society of London watched with enormous interest. Here was something genuinely new. Something that shouldn't have been possible by the old framework. Something that suggested blood could be moved between living bodies without killing them. Suddenly, The question became obvious. What if this worked in humans? Jean-Baptiste Denis thought it would. Denis was physician to Louis XIV, which gave him both resources and a degree of confidence that bordered on recklessness. He had watched Lau's dog experiments. He had read everything available, and he had decided that animal blood, specifically the blood of gentle animals, might carry therapeutic properties beyond simple fluid replacement. He chose lamb's blood deliberately. The lamb was calm, peaceful. He believed those qualities might transfer to the patient along with the blood. This wasn't considered eccentric at the time. It was the extension of a framework in which blood carried identity, character, and something close to spirit. Robert Boyle, one of the founders of modern chemistry, had seriously wondered whether a coward's blood transfused into a brave man might make him fearful, whether the memories of a donor might follow his blood into a recipient. These weren't fringe ideas. This was what serious, educated men believed about blood in 1667. Denis performed his first transfusion that summer. The 15-year-old boy with the fever received 12 ounces of lamb's blood through a quill tube. He survived. Denis performed several more transfusions in the months that followed. Most patients lived, which told you more about the small volumes used and the stubbornness of the human immune system than about any correct principle Denis had identified. Then came Antoine. Marbury's wife brought him to Denis because he was violent, unpredictable, and had reportedly tried to set buildings on fire. She hoped that gentle animal blood might calm his temperament. Denis transfused him twice with calf's blood. After the first transfusion, Marbury seemed quieter. After the second, everything collapsed. A violent fever hit him suddenly. His urine turned black. His body shook. He nearly died. He recovered from that episode. Then, weeks later, he died under circumstances the historical record still hasn't fully untangled. His wife was accused of poisoning him. She stood trial. She was acquitted. The evidence suggests she may actually have been giving him arsenic before Denis ever got involved, and that Denis's second transfusion had independently nearly killed him from causes nobody could identify. The French authorities banned transfusion. The Royal Society in England quietly dropped their experiments. Pope Innocent XI issued a condemnation. The practice went underground and then went silent. 150 years of silence. But here is what nobody in that Paris room understood. The black urine wasn't mysterious. It had a precise biological explanation. Marbury's immune system had recognized the calf's blood as foreign. It had attacked the invading cells and destroyed them. The destruction released hemoglobin into the bloodstream. The kidneys, overwhelmed, tried to filter it out. That was the black urine. That was the body fighting back against something it correctly identified as not belonging there. A large enough dose of that foreign blood would have killed him as surely as a blade. Not because Denis made a mistake. Not because the equipment failed. Because the immunological distance between a calf and a human being made their blood fundamentally incompatible. Any amount of careful technique would have produced the same result. The problem wasn't the procedure. The problem was invisible, built into the blood itself, and utterly beyond the reach of any framework available in 1668. The silence lasted until 1818. Then James Blundell broke it. Blundell was a London obstetrician. He watched women die of postpartum hemorrhage. He found it intolerable. He had read the 17th century experiments. He had noticed that the animal-to-human transfusions consistently failed while some of the human-to-human attempts had survived. He drew the right conclusion. Human-to-human was physiologically more feasible, and he built equipment to test it. His transfusion apparatus used a syringe system, fast enough to deliver blood before clotting could stop the procedure. He performed 10 transfusions between 1818 and 1829. 5 patients died. 5 survived. All 10 had been in immediate danger of death from hemorrhage before he began to be wide the standards of the time. 5 survivors was extraordinary. By any honest standard, 5 deaths was a catastrophe. But Blundell couldn't explain the pattern. He attributed the difference to patient condition, to procedural quality, to factors he could observe and adjust. The real variable was invisible. His 5 survivors happened to receive blood that was immunologically compatible with their own. His 5 who died received blood that wasn't. He had no way to know this. Nobody did. Meanwhile, the clotting problem remained. Blood began to clot within minutes of leaving the body. The window for successful transfusion was narrow and unforgiving. Physicians across Europe spent decades trying to solve it. The solutions ranged from clever to deeply strange. Some tried direct transfusion, connecting donor and recipient with rubber tubes and racing to complete the transfer before clotting began. Others tried removing the clotting factors entirely by whipping collected blood with bundles of twigs until the fibrin adhered to the twigs and left the remaining blood unable to clot. The results were unpredictable. The process was chaotic. The outcomes were inconsistent in ways that resisted any systematic explanation. Then some physicians proposed something that moved from experimental into genuinely extraordinary territory: milk transfusion. Between 1873 and roughly 1884, a non-trivial number of physicians in North America and Europe injected milk directly into patients' veins as a substitute for blood. Cow's milk mainly, occasionally human breast milk. The rationale, articulated by Thomas Gordon in London and by physicians including Joseph Howe in North America, went like this. Milk, once injected into the bloodstream, would be converted by the body into white blood cells, which would then become red blood cells, restoring lost volume. This theory had no biological basis whatsoever. It was constructed from the observation that milk and blood both nourished, from a vague theory of cellular transformation, and from the general 19th century habit of building elaborate physiological frameworks from first principles when actual observation was unavailable or inconvenient. Here is the thing that makes milk transfusion genuinely instructive rather than simply absurd. It didn't always kill patients immediately. Milk injected intravenously does temporarily expand blood volume because it adds fluid to the circulatory system, something like an extremely primitive saline drip. Some patients survived the procedure. This was interpreted as evidence that it worked. The violent fever, the chills, the vomiting that followed milk transfusion in almost every case were interpreted as evidence that the therapeutic process was underway, that the milk was transforming, that the body was doing its necessary work. What the body was actually doing was mounting a furious inflammatory response to a foreign substance that had absolutely no business being in a blood vessel. The physicians watching this happen saw improvement where there was crisis, progress where there was attack. The practice faded not because anyone proved it was harmful, but because the results were too inconsistent and the patient experience too unpleasant to sustain enthusiasm. Saline solution had emerged as a safer volume expander. The urgency diminished. The field moved on, and then, in 1900, Karl Landsteiner went to work. Landsteiner was 32 years old. He worked at the Vienna Pathological Institute with the quiet, methodical precision of a man who trusted observation over theory. He took blood samples from himself and 5 colleagues. He separated the red blood cells from the serum in each sample. Then he mixed every person's cells with every other person's serum, working through all possible combinations systematically. What he saw stopped him. Some combinations were fine. The cells floated freely in the serum. Nothing happened. But other combinations produced something dramatic. The red blood cells clumped together suddenly, forming visible masses in the dish. The pattern wasn't random. It repeated consistently across every combination he tested. A, B, and C. What would later be renamed O. 3 groups. Predictable. Systematic. A biological architecture hiding in plain sight inside every drop of human blood. In 1902. His colleagues Alfred von de Castello and Adriano Sterler identified the 4th group, AB. The system was complete. The mechanism was this. Red blood cells carry proteins on their surface called antigens. These are identification markers that the immune system uses to distinguish self from foreign. Blood serum carries antibodies, proteins designed to recognize and attack foreign antigens. A person with type of blood carries antigens on their red cells and anti-B antibodies in their serum. If type B blood enters a type of body, the anti-B antibodies attack the incoming cells immediately. They clump them together, then destroy them. The destruction releases hemoglobin into the bloodstream. The kidneys work frantically to filter it out. That is what the black urine was. That is what had been killing transfusion patients for 230 years. Finally, there was an explanation. Landsteiner published his findings in 1901. He was not dramatic about it. He described the observations methodically. He noted, almost as a footnote, that the results might be relevant to understanding transfusion reactions. The medical world did not immediately celebrate. The connection between a laboratory observation and clinical practice at the bedside took years to fully work out. Rubin Ottenberg connected the dots first. In 1907, working in an American hospital, Ottenberg typed both donor and recipient before performing a transfusion. He confirmed compatibility. Then he proceeded. His patients survived at dramatically higher rates than transfusion patients had ever survived before. The improvement was immediate and measurable. It should have triggered instant universal adoption. It didn't. Clinical practice absorbs even the most powerful discoveries slowly, especially when changing requires equipment, training, and institutional will. Blood typing before transfusion didn't become standard in American hospitals until the First World War made the cost of ignoring it impossible to bear. Suddenly, the Western Front changed everything. Soldiers bled to death in numbers that made theoretical objections irrelevant. Field surgeons needed blood. They needed it faster than any existing system could supply. Oswald Robertson, an American physician attached to the British Expeditionary Force, built the first blood bank in 1917. He collected type O blood from donors behind the lines, stored it in citrated solution to prevent clotting, and transported it forward to casualty clearing stations. Citrate, recently identified as a safe anticoagulant, solved the clotting problem that had haunted transfusion medicine for a century. Refrigeration extended storage to 4 weeks. Robertson's system began saving lives at a rate that was immediately measurable, and the military adopted it at scale. By the end of the First World War, blood transfusion had transformed from a procedure with roughly 50% mortality into one that was saving lives across European battlefields. Not through any single dramatic breakthrough, but through the convergence of blood typing, anticoagulation, refrigeration, and the organizational infrastructure of an institution willing to move fast when lives depended on it. The first civilian blood bank opened in Leningrad in 1932. Cook County Hospital in Chicago opened the first American one in 1937. Then, the Second World War expanded the system to global scale, with blood collection drives across allied countries generating millions of units for military use. Meanwhile, Charles Drew built the systems that made it all work. Drew was a black American physician who developed the blood banking techniques used by the American Red Cross during the Second World War. He organized the collection programs that supplied Allied forces. He refined storage methods, improved protocols, and created an infrastructure that saved thousands of lives. Then the American Red Cross segregated the blood supply by race, labeling blood from black donors separately and refusing to mix it with blood from white donors. There was no scientific basis for this policy. None. The blood types Landsteiner had identified were distributed across all races without any meaningful racial pattern. A type O positive unit of blood from a black donor was immunologically identical to a type O positive unit from a white donor. The segregation was entirely political, dressed up in the language of reassuring donors, and Drew said so publicly. He resigned from the program in protest. The irony that the man who made modern blood banking possible was denied a desegregated unit of blood by the institution he had built is a particular kind of American historical irony that does not get better the longer you look at it. Karl Landsteiner won the Nobel Prize in Physiology or Medicine in 1930. 30 years after 6 glass dishes in a Vienna laboratory produced the observation that explained 2 centuries of transfusion deaths. He continued working until virtually the last day of his life. On June 24, 1943, he suffered a heart attack at his bench at the Rockefeller Institute in New York. He died 2 days later, having received a transfusion during his final illness, safely matched to his blood type using the system he had spent his career building. Jean-Baptiste Denis pumped lamb's blood into a feverish boy in 1667 because he had no other option. Because the framework available to him suggested it might help. Because the thing that was actually killing his patients was invisible to him and would remain invisible for 2 more centuries. He was wrong about almost everything. The lamb's temperament didn't transfer. The animal blood wasn't therapeutic. The logic that made the procedure seem sensible was built on foundations that wouldn't survive serious scrutiny, but underneath all of it, buried beneath 230 years of wrong answers and desperate improvisation, his fundamental intuition held. Blood lost could be blood replaced. Life could be returned to a body losing it. He just had no way of knowing how right he was, or how long it would take for anyone else to find out. In the end, it took 6 glass dishes, 1 quiet Austrian physician, and a Nobel Prize 30 years overdue.